All right, welcome, welcome, ladies and gentlemen. This is the video on determining delta H using through calorimetry, and this is our third flip lesson in the thermochemistry unit. This one, there's a little more that I have to talk about in terms of the lecture stuff before we see a sample problem. But calorimetry you are actually already familiar with because you've already done the the solution stoichiometry lab, where you had your acid and your base and you combined them and you noticed, hey, there was a temperature change there. So you are already somewhat familiar with this technique. Calorimetry, the definition of the term is very simple. It's the science of measuring heat. That's all it is. And all fundamental calorimetry experiments involve this main idea. Two species are combined in the same container, so it could be two different things. We did the acid and the base, could be a piece of metal and water. Excuse me. And you measure the temperature change. That's the idea behind all calorimetry. So you have already done this one. You've already done this, using calorimetry to look at an acid-base reaction. We just weren't necessarily looking at it from determining delta H of that reaction. We were using it for stoichiometry purposes, but you were still doing calorimetry there. The main assumption in all calorimetry experiments is this statement at the bottom, that your species that are in your insulated container, your acid and your base, the water that surrounds it, the piece of hot metal and the water that it's in, heat lost will always be equal to heat gained. Sometimes this assumption is a little problematic. Sometimes we get some leakage, but realistically, we're going to sort of assume that we're working under perfect conditions, where if one thing is losing heat, something else in that simplified calorimeter, the coffee cup calorimeter, is gaining that heat. Heat lost is equal to heat gained. So calorimetry experiments, you've already done this, and I do want to stress that to you. You've already done a calorimetry experiment. We just didn't call it that. Coffee cup calorimeter, 2 styrofoam cups. You have your system, right, which is in your cup that you're interested in examining, and you have a thermometer that's in the system that's monitoring temperature changes. And that's it. That's really, calorimetry is pretty straightforward. But there's something that we do have to discuss with calorimetry experiments. If two reactants at the same temperature are mixed and the resulting solution gets warmer, this means that the reaction taking place is exothermic. We have to talk about that for a little bit, because while at first glance you go, well, yeah, it makes sense, if upon deeper glance you need to consider it. So reactions taking place, same temperature, we mix them, and the resulting solution gets warmer. Okay, resulting solution. Exothermic means that your reaction releases heat. And we should all agree with that. We're comfortable with that term. But if the solution is getting warmer, then if you're thinking about this and you're like, but wait a second, if it releases heat, shouldn't then the system get colder, not warmer? And I agree, it has to do with the perspective. So the resulting solution, that's your surroundings. The reaction that's taking place is the system. But the solution itself, think about it, the main component of every single solution that we're going to look at in AP chemistry is water. That's the main component of every single solution. Even some of our concentrated acids and concentrated base solutions, by far and away, the number one thing that's in those solutions is water, not the acid or the base. So water is going to not be part of the chemical reaction, but it's going to be part of the surroundings. However, think about what you're measuring with your thermometer. Your thermometer, which you have in there, that is measuring the fact that a solution got warmer, the thermometer is really measuring the surroundings, realistically. Right? Your thermometer it's not really measuring the actual chemical reaction that's taking place. It's measuring the temperature of the water that is surrounding the chemical reaction. So your thermometer, it's measuring the surroundings. So when we say that we combine two reactants in a container and we monitor the solution, what we're really doing is monitoring the surroundings. And we notice that the temperature of the solution goes up. Well, the temperature of the solution had to go up because the chemical reaction released heat into the solution. The solution as a whole, it's mostly water, so it's mostly surroundings. It's not actually mostly the system. So that increase in your solution of temperature is due to your reaction being exothermic. And then the opposite is true. An endothermic reaction will cause a decrease in temperature of the surroundings because the surroundings are what you are measuring. The surroundings are what you are monitoring. It's almost always going to be easier to monitor what happens to the surroundings of a chemical reaction than to monitor what's actually happening in the reaction itself, especially in terms of calorimetry. Your surroundings got colder because your endothermic reaction absorbed heat from the water that was surrounding it and made the temperature of the water drop. So that's a huge, huge thing to think about. But anytime you're told a temperature change in a calorimetry experiment, it's almost always going to be the temperature change of the surroundings because that is what we can measure. You're measuring the temperature change of the water, not necessarily the temperature change of the reaction itself, or not directly the temperature change of the reaction itself. So that's a big, big idea that we're going to carry through with us in our discussion of calorimetry. Some terms with calorimetry: heat capacity. So heat capacity is a pretty simple idea. It's like the name sort of implies, what is the capacity of your substance to withstand heat? Meaning, how much heat is required to heat something up to different temperatures or cool it down to, or how much heat does it have to lose to get cooled down to lower temperatures. Amount of heat required to raise the temperature of something. That's all it is. Now, specific heat capacity, you saw this in reagents, right? This is C. Energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So we have this sort of tie-in. Heat capacity is very general. How much heat does it take to raise the temperature of something? Specific heat capacity, we're adding some numbers in. We're saying, okay, we're going to only look at 1 gram of a thing. Specific heat capacity is always going to be 1 gram. And we're going to figure out how much heat is required to raise the temperature just 1 degree Celsius. So we have these units of joules per gram degree Celsius. How many joules does it take to raise the temperature of 1 gram of something 1 degree Celsius? Joules per gram degree Celsius. Highly related to specific heat is molar heat. Molar heat capacity, which is the exact same idea. It is the exact same idea, except we are talking now about 1 mole of a substance, but we still have the 1 degree Celsius bit. So hopefully you are kind of understanding that the relationship between specific heat capacity, which is joules per gram degree Celsius, and molar heat capacity, which is joules per mole degree Celsius, what is it that's linking these two? That's right, gram formula of mass, right? Just converting between grams and moles, we have this linking. Hey, it pops up everywhere, right? We have this link between specific heat and molar heat capacity simply through, hey, turning grams into moles, and we have this exact same idea. Now, calorimetry with heat capacity. So heat capacity, thinking about this generally and not really using it mathematically, substances that have larger specific heats. What that means is, okay, it takes more joules to raise the temperature of 1 gram of something by 1 degree. That's what it means. That's a definition of specific heat capacity. Larger specific heat means it takes more energy to raise the temperature of the same amount of that sucker. It takes more energy to heat it up. Metals typically have significantly lower heat capacities than water. Water has an extraordinarily high heat capacity. Oh my goodness, water specific heat is an enormous number. Most other substances are somewhere in the 1.3 and lower, and water's is almost 4.2. I mean, that's a crazy number. That's a huge number. That is why it takes forever to get water to boil, because you have to add tons of energy into your sample of water in order to raise its temperature up to the boiling point. Just because you apply the same amount of heat to 2 different substances does not mean that you will get the same temperature change for those two substances. No, 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 no. Temperature is not heat. They're related, they are highly related, but they are not the same thing. We look at this example with water and copper. If I had 4 joules and I added 4 joules into 1 gram of water, I could only raise the temperature of the water 1 degree Celsius. But if I take the same 4 joules and apply it to 1 gram of copper, now I'm going to be able to raise the temperature of that 1 gram over 10 degrees Celsius. So the same amount of heat being applied to 2 samples does not mean that you're going to get the same temperature change. You have to consider their specific heats. Things with larger specific heats take way more energy to increase their temperature. And also, masses, amounts, matter. Because specific heat is saying this is how many joules per 1 gram, if you had 10 grams of water versus 100 grams of water, well, now you have multiplied by 10 how much heat you need to add to that to get the entire sample raised up. So masses matter, and the value of specific heat matters as well. Calculating delta H via calorimetry. Well, we pull in a big equation from Regents, Q equals mc delta T, which hopefully everyone remembers. I mean, that's a big one. Use that one a lot in Regents Chem. So we have Q, that's heat. We have M, that's mass. We have C, that's specific heat, joules per gram degree Celsius, and the change in temperature. How much energy is going to take to raise a certain sample to a certain temperature. And then vice versa. Delta T, right? Delta means change in. It's always final minus initial. Always. Always. It is not necessarily big number minus small number. No, it's final temp minus initial temp. You can absolutely have a negative value for delta T. You absolutely can. It just means that your final temperature was lower than your initial temperature. That's all it means. And guess what? If you have a negative delta T, you're going to get a negative Q. And what does that mean? Oh, that means heat was released. Oh, so the temperature dropped because it was releasing that heat out into the surroundings, so it doesn't have that heat anymore. Oh, so yes, we can have a negative delta T, means we're going to get a negative Q, indicates that we are having an exothermic process on our hands. We also have molar heat, because after all, we have molar heat capacity. Look at it. It's the same, almost. Almost. N is our abbreviation is our 1-letter abbreviation for moles. Basically, we were out of M's. We had too many M's in other places, so we had to go to N for moles. But it works exactly the same way in terms of we're just multiplying our molar heat capacity by our change in temperature by our amount of moles to figure out heat. Now, a big thing that we have to be aware of whenever we're using either of these formulas, units have to agree. Units have to agree. Units have to agree, meaning you are mandated essentially by the unit for specific heat and molar heat. If you're using specific heat, you have to have heat in joules, you have to have mass in grams, and you have to have temperature in degrees Celsius, which is not really going to be problematic for us. But joules and grams, not kilojoules, not kilograms. So if you're given mass in kilograms, convert it, put it in grams. If you are plugging Q in to solve for something else, to solve for M, or to solve for C, convert kilojoules to joules first, because the units have to agree. I'm going to be yelling at you all year long about units agreeing. Swear to God, all year long, units have to agree always. But what we really want to do is determine delta H through calorimetry. Q isn't enthalpy. All enthalpies are heat. Not all heats are enthalpies. We've talked about this. And enthalpy is very specific. Enthalpy is the Q released in a chemical reaction, but remember it's tied to the molar ratio. So we have this per mole component of enthalpy that is kind of lacking when we're just looking at Q, because Q is just heat. Q is just joules, kilojoules. That's all it is. It's just kilojoules. It's not the same thing as enthalpy. If you have salt for Q, you do not have your delta H value. Now the nice thing is you're very close to getting your delta H value. So our strategy, if we are asked to determine delta H and we had to use some Q equals MC delta T, is to recognize that delta H is this, kilojoules per mole of reaction. Just like molar mass, gram formula mass is really just grams divided by moles, and then that's it, and then you've solved it. Much in the same way, delta H is just kilojoules divided by moles. So we're going to have this strategy of find kilojoules, find moles, divide the two, and kablamo, you have your delta H of reaction. So just putting that all up here. You will typically want to do Q equals MC delta T. That will give you kilojoules. So this bit is going here if we're solving for delta H using calorimetry. The Q equals MC delta T, that gets you your kilojoules value. Then you have to figure out the moles of reaction. The way you do that is calculate moles of one reactant. One. Not all. No, not all. You're not finding moles of everything and adding them together. Because remember, delta H is tied to the coefficients. It's not tied to all of them at once. It's tied to them individually. It's for that particular mole ratio. It's for 2 moles of water making 1 mole of O2 and 2 moles of H2. So it's tied to the 2 moles for the water. So find moles of one reactant and put it on the bottom. Divide them, and that's all you need to do. That's your delta H. And we're going to go through a practice problem. I will add, if you're taking notes on this problem, which I strongly want you to do, there's going to be a lot of writing, so at some point I'm going to have to erase what I have to make room for the new stuff. Yay, lots of writing. In a coffee cup calorimeter, 50 mils of 0.1 molar silver nitrate solution and 50 mils of 0.1 molar hydrochloric acid solution are mixed to form the precipitate AgCl. The two solutions were initially at 22.60 degrees Celsius, and the final temperature is 23.40 degrees Celsius. Calculate the delta H of the reaction. This is very typical calorimetry from delta H problem. I will also add AP loves questions like this. Oh, they love it. I have seen this on the first response lots of times. Now, the nice thing is when this is on the first response, it's usually not just, hey, here's all your information and solve it in one step. Usually they'll ask you kind of leading questions, like there'll be a part A, hey, is this exothermic or endothermic? Part B, how many moles were involved, and then part C, how many kilojoules were involved? And then part D, what's the delta H? So they kind of lead you through the process a little bit, which is nice, but we're going to do this all in one go. Then we have some assumptions which are also important. Assume that the density of the solution is the same as that of water, and that the specific heat of the solution is 4.18 joules per gram degree Celsius. Hey, that's the same as water. And that the heat absorbed by the calorimeter is negligible. So, this last bit. What this is saying is that heat lost is equal to heat gained. We are going to assume that heat was transferred perfectly here. That's what that is telling you. Assume that the heat lost by the calorimeter is negligible. It means we're going to assume that heat was perfectly transferred. A good place to start in this problem. There's a lot of numbers. There's a lot of things going on. You know where a great place to start is? If you said write a reaction, ding, 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 give yourself a prize. Let's figure out the reaction that's going on just so we can kind of organize all this stuff. So we got silver nitrate and we have hydrochloric acid, and we're making the precipitate AgCl. This is a double replacement reaction, so hopefully you can figure out that the other product is going to be HNO3. Now, let's organize our numbers. It says that we have 50 milliliters of AgNO3, and it's 0.1 molar. And we also have 50 milliliters of HCl, and it is also 0.1 molar. I will add at this point too, I did not balance this equation because it was already balanced. So it is balanced as is. Everything is in a 1 to 1 to 1 to 1 ratio, right? It's 1 to 1 to 1 to 1. And that's our precipitate. All right, so we have 50 mils of the 0.1 molar for both reactants. And then what other information do we have? Well, we have an initial temp of 22.60 degrees Celsius, and we have a final temp of 23.40 degrees Celsius. Great, they told us that. They said, assume the density of solution is the same as that of water. You should know the density of water. Density of water is 1 gram per milliliter. Thank you, Smartboard, for making me write like a 3-year-old. 1 gram per milliliter. There we go. That's better. And that specific heat of the solution is the same as that of water, 4.18 joules per gram degree Celsius. So we have a TI, initial temperature, 22.60 degrees Celsius. We have a final temperature, 23.40 degrees Celsius. We have density, 1 gram per mil. And we have specific heat, 4.18 joules per gram degree Celsius. So basically, these are all the numbers that the problem has given us. You'll notice that I kind of grouped them together in different ways, because if you look at all of these numbers over here, all of these numbers are numbers that relate to Q equals MC delta T. We have a TI and TF. That's our delta T. We have a C value. They gave us density, 1 gram per milliliter. That's a relationship to mass, right? We can use this to get mass. So all of these values, the TI, TF, the density, and the specific heat, they're things that relate to Q equals MC delta T. And then we look over here at these values. Volume and molarity. Volume and molarity. They gave you volume and they gave you molarity, which means what did they really give you? Moles! They really give you moles. That's what they gave you. So look at this information that we have. They gave us a whole bunch of numbers that are for Q equals MC delta T, and then they gave us numbers that are for moles. What are they asking about? They're asking about delta H. What are the units on delta H? Kilojoules per mole of reaction. Find a way to get kilojoules, find a way to get moles, divide the two, that's your delta H. So that is exactly what we're going to do. We're going to use these numbers here to get Q equals MC delta T. That's going to be our kilojoules. We're going to use these numbers here to get per mole of reaction. That's going to go on the bottom, divide them, and then we're good. I'm going to talk about the mole bit first. So we're going to come back to Q equals MC delta T. So let's figure out how many moles we have. Honestly, I'm not even going to write it up because I'm confident that at this point we can use the molarity definition to get moles of each one. And you work out that you have 0.005 moles of both silver nitrate and hydrochloric acid. Want to point this out. These guys are in a 1-to-1, right? They're reacting in a 1-to-1 ratio. Oh, look, we have the same amount of moles of each one. This means that there's no limiting reactant, that everything is getting used up. So they're both completely consumed, but you only want moles of one species when you're finding, when you're calculating delta H. So for us, the per mole of reaction is going to be 0.005. Right? Because 1 mole of silver nitrate plus 1 mole of hydrochloric acid. So we're not going to add them together because that would be the equivalent of adding coefficients, and we don't do that. It's this ratio of one of these guys reacts with one of these guys. It's not saying, hey, it's 2 because 1 plus 1 is 2. No, no, no. They're in a 1-to-1. So if I have 0.005 moles of one thing, I know it needs 0.005 moles of something else. This is going to be my per mole of reaction. I'm not going to add them together. You only want moles of one thing. So that's great. That gives me that value that I'm going to need in delta H equals kilojoules over per mole of reaction, the 0.005 moles. That's my per mole of reaction. Great. Now let's do the Q equals MC delta T bit. Have to erase a lot for this. Hope you got that. If not, rewind it and write it down. Q equals MC delta T. Okay. Well, I have C. That's 4.18. The problem told me to assume that the specific heat of the solution was the same as that of water. Great. Delta T, final minus initial. The final temperature was 23.40 degrees Celsius. The initial temperature was 22.60 degrees Celsius. Mass. Okay, what's that going to be? Here's where you have to consider the entire thing in the calorimeter. So for mass, what's in the calorimeter? And in the calorimeter, we have 50 mils of one thing and 50 mils of something else. So we have a total of 100 milliliters in the calorimeter. And that's the thing that had the temperature change, right? The 100 milliliter thing had that temperature change. So I want the whole thing. But 100 milliliters is not a mass. Ah, but density. 1 gram per milliliter. It told me to assume that the solution's density was the same as that of water, 1 gram per milliliter. So 100 milliliters will have a mass of, 100 grams. I need the whole thing because the whole thing underwent this temperature change, but so I'm going to plug in 100 grams right here. You'll notice that units will cancel. The grams in the mass cancels with the grams in the bottom of specific heat. The degrees Celsius here will cancel with the degrees Celsius there and leave you with joules. Units must agree. All works out nice. You could actually do this in a T-chart, and I have had students do this with a T-chart because realistically Q equals MC delta T is not really a mathematical formula. It's really just getting units to cancel. That's all it is. So doing that math, we get a Q value of positive 334.4 joules. Right? Everyone should agree with me. That's the Q value that you get. Stop, think, reflect. What does a positive Q value mean? A positive Q value means an endothermic process. What is the definition of an endothermic process? One that absorbs heat from the surroundings. So why, if in this case where our temperature went up, or which means exothermic, by the way, remember the temperature went up, so it's exothermic. So why are we getting a positive Q value? Because you're not measuring the change in temperature of the reaction. This right here is your heat gained by the water that's in this calorimeter, because that is the #1 component in that calorimeter. So you put a thermometer in, that is what the thermometer is measuring. That value, the positive 334 joules, that is the heat that is gained by the water. Why did the water gain that much heat? Because the reaction must have lost that much heat. The reaction must have lost 334.4 joules worth of heat in order for the water to gain 334.4 joules of heat. That Q that you get from Q equals MC delta T in a calorimetry problem is not for the reaction itself, it is for the surroundings. It is the heat that the surroundings exchanged, which we then go, oh, okay, it must have come from the reaction. This makes a lot more sense now. If our reaction released that much heat to its surroundings, of course the surroundings temperature went up. So this is why we know that if we get that positive value for Q, you have to think about it and say, well, okay, that's for the surroundings. Flip the sign for the system. Now, that's our joules. In kilojoules, this would be minus 0.3344 kilojoules. We are now ready to finally calculate our delta H value. Again, delta H, this is the easy part. Kilojoules per mole reaction. We said the kilojoules was minus 0.3344. We said the per mole reaction, 0.005. Right? One thing, not adding them together, just one. Divide the two, we get a negative 66.9 kilojoules per mole reaction. You get 1 point for the correct answer. The correct answer must be correct numerically. It must also have the correct sign. You invert your sign because you're not thinking about what's happening with the system versus the surroundings. You don't get that point on the AP chemistry exam, and that's a dangerous position to be in. So constantly be thinking about, in calorimetry, direction, and we're measuring what exactly? We're measuring the temperature of the system or the temperature of the surroundings, and then be thinking about that. So that's delta H using calorimetry. You're going to do plenty of practice problems like this for me in class and answer calorimetry problems.